Hello everyone. Today in this lecture we will continue our discussion on MOSFET IV characteristics, and in the previous lecture, if you recall, we have seen how we can understand the IV characteristics of the MOSFET, and we discussed that there are three important regimes in MOSFET IV characteristics. One is the linear region, second is the saturation region, and third is the subthreshold region. Okay. So, and all this can also be understood from the band diagram picture of the MOSFET, which in which the MOSFET is, or MOSFET looks like a barrier control device. So, if we draw the band diagram of the MOSFET across the channel, the MOSFET looks like a barrier controlled device, and the barrier in the channel can be controlled in this way. So, the gate voltage essentially lowers the barrier or increases the barrier. The drain voltage allows electrons from the source side to cross the barrier and start a current in the system. So, that is how it looks like, and we also have seen in our previous discussions that the general form of the current can be written down in this way, where the current is a product of the charge in the channel, the charge density, charge per unit area, times the average velocity at which this charge is moving through the channel, and multiplied by the width of the channel. So, these three things essentially. Out of this, W is geometry dependent. We can change it by changing the dimension of the transistor. This Qn depends on the electrostatics. This Qn actually is governed by the electrostatics of the MOSFET, which in turn depends on the gate voltage and the drain voltage, and this velocity in long channel MOSFETs, this velocity, the velocity of any charged particle is given as this. In short channel MOSFET, this will be a ballistic velocity. Okay. So, in the long channel MOSFET, this velocity is dependent on the, velocity is also a factor of the scattering that is happening in the channel, and it is directly proportional to the electric field. But what happens is, as soon as this electric field becomes too high, electric field in the channel is around of the order of 10 kilovolt per centimeter. In that case, the velocity is no longer linearly dependent on the electric field, and the velocity starts saturating after this value of the, typically after this value of the electric field, and that phenomenon is known as the velocity saturation, and that is one of the contributors of saturation current in the output characteristics of the MOSFET. The second contributor is the pinch off in the channel because of the high drain voltage. Okay. In ballistic MOSFETs, however, the velocity does not saturate. Even then the current saturates, and we will try to see how, or we will try to understand how that happens later on while we discuss the transport theory in nano MOSFETs. Okay. So, this is the background, or this is sort of what we have seen so far. So, let us see. So, we have gone through the output characteristics of the MOSFET. The second important IV characteristics of the MOSFET is the transfer characteristics, and we will have a qualitative understanding at the moment. Later on we will also see the quantitative treatment of IV characteristics, especially the output characteristics. Okay. So, the transfer characteristics, as we have seen in the last class, is the dependence of IDS on VGS for a fixed voltage, for a fixed VDS essentially. And this, the idea of this we can take, or this the transfer characteristics in some way we can also deduce it from the output characteristics. So, so this is the barrier structure in the MOSFET, and effect of drain and gate voltage on the barrier. The gate voltage is lowering the barrier, the drain voltage is creating an asymmetric barrier which is inducing, or which is producing a current in the channel. This is the output characteristics that we have seen, that we have discussed, and just to sort of point it out here, this is typically the symbol of the MOSFET, the N MOSFET. Okay, we have a gate terminal. This is how we write it down in circuits: the gate, the drain, and the source. Okay, the current direction is shown from drain to source, which means electrons are flowing from the source to drain. Okay, so in the output characteristics, as you know now, that there is this linear regime, there is this saturation regime, and there is this subthreshold regime. And if we want to understand the transfer characteristics, which is essentially the IDS versus VGS, IDS as a function of VGS, IDS for a constant VDS. So let's take the case of an arbitrary VDS. So for an arbitrary value of VDS, for an arbitrary drain voltage, what happens is when the gate voltage is extremely small, in that case this channel in the MOSFET is not formed. So generally this is how the MOSFET looks like. This is the source, the drain, and we have a channel here. This is the channel, and only after a certain value of the gate voltage, only after the threshold voltage, this channel or the significant charge starts appearing in the channel just below the oxide, so that the MOSFET can conduct. So before this voltage, which is also known as threshold voltage, before the threshold voltage, the current IDS is extremely small, whatever be the drain voltage. Okay, so if this is VTH, this current will be extremely small, whatever be the value of the VDS. It is not too much dependent on VDS at the moment. As soon as the gate voltage is above the threshold voltage, let's assume the source is grounded, we have a voltage applied on the drain terminal, we have a voltage applied on the gate terminal as well, VGS. As soon as VGS is above VT, the threshold voltage, what happens is that now the current conduction starts, and it is also dependent on the VDS. So for an arbitrary VDS, the current will increase, and so typically in this way. So for small VDS it will be like this, for large VDS it will be a an exponential kind of increase. So this is VDS1, this is VDS2, and VDS2 is greater than VDS1. Okay. This current IDS, if we closely look here in this picture, in this barrier picture, the IDS is the current because of electrons going from the source side to the drain side. So that depends on the height of the barrier from the source side. So if the gate voltage is 0, this is the height of the barrier. If the gate voltage is, let's say, some positive value above VT, it is the height of the barrier is reduced, and it is this value. Okay, so more the height of the barrier, less will be the probability of crossing the barrier by the electrons on the source side, and it is an exponential relationship, which I guess if you are familiar with p-n junction theory, you can also deduce it from there. So this current from the source side or from left to right is directly proportional to the or exponential minus ESB, where SB is the barrier height from source side. Okay, so that's why if we increase VGS further, it is almost like an exponential increase in the current. Okay, for small VDS it will not be so sharp, but for large VDS it will be a very sharp exponential. It will be just very sharp exponential. Okay. So this is the transfer characteristics of the MOSFET. Generally, the transfer characteristics is important. So this is plotted here. In the transfer characteristics, the regime below the threshold voltage is known as the subthreshold regime. So this regime is the subthreshold regime, and the transfer characteristics is important in understanding the subthreshold regime of the MOSFET. Okay. And the subthreshold regime is important in trying to understand the gate control on the MOSFET. What do we mean by gate control here? So it means that how effectively the gate is able to control the channel in the MOSFET. That is broadly known as the gate control. And in the subthreshold regime, by understanding the current relationship between the current IDS and VGS, we can see how quickly IDS increases if we increase VGS slightly. And that is the gate control. If we increase gate voltage slightly, how quickly the channel is getting formed, how quickly we are switching on the MOSFET, how quickly the current is increasing. So that's why this regime is extremely important in trying to understand the subthreshold characteristics. And in some modern day applications, some devices are biased very close to the threshold region, threshold voltage on the gate terminal. Okay, and particularly in those devices, this is a very important regime to understand. The subthreshold regime is an extremely important regime to understand. Okay. So this is about the IV characteristics, and we have taken an extremely qualitative approach in order to understand the IV characteristics of the MOSFET. The output characteristics is IDS versus VDS. It has three regimes: linear, saturation, subthreshold. The transfer characteristics has an extremely important regime, which is the subthreshold regime, and after the subthreshold regime, or this subthreshold regime tells us about the how effectively the gate is controlling the channel. After that, it tells us about the effect of the drain voltage on the current. Okay. Now let's try to have some quantitative understanding of how current is related to various voltages in these MOSFETs. Okay. So there is a conventional theory of IV characteristic, conventional way of calculating the IV characteristics of the MOSFET. We'll also do that quickly, but before going into that, let's quickly see how IDS is related to the various voltages that are applied in the MOSFET, how IDS is related to VDS and VGS. And in this, we'll take this barrier picture. We'll start with this barrier picture of the MOSFET, in which there is a barrier in the channel, and this barrier is controlled by the barrier height is controlled by the gate voltage, and this barrier symmetry, so to say, is controlled by the drain voltage. Okay. And as we know that both source and drain are they are n-type materials, so they have electrons, enough electrons there, and similarly the source and the drain will also have enough electrons in it. Okay. So both electrons on both sides will have certain probability of crossing the barrier and reach to the other side. So there will be a current from source to drain, from left to right in this way. This is represented as ILR, the current from left direction to the right direction, and there will be a current from right to left This is because of the electron movement from the source side to the drain side. And the net current in the MOSFET IDS, or let's not just let's say this IDS will be ILR minus IRL. Okay, so if left to right current is more, in that case IDS will be positive, and if right to left current is more as compared to left to right current, in that case IDS will be negative, which means current will be from drain side to the source side. Generally in MOSFETs, just to sort of remind you about the convention, the direction from the source to the drain is taken to be the x direction, and the direction from gate to the channel is taken to be the y direction. That is typically how it is represented. So with this, we are trying to see quantitatively, we are trying to understand how the current is dependent on various voltages. So as we know that from our basic semiconductor physics, the probability that an electron sitting on the source side will cross the barrier is directly proportional to the exponential of the height of the barrier. So if ESB is the height of the barrier from source side which means essentially this height, and EDB is the height of the barrier from the drain side. Which means it will be this height. So this will be EDB and this will be ESB. So the number of electrons crossing from left to right, and as a consequence the current from left to right, or the current because of the electrons crossing from left to right, will be directly proportional to exponential minus ESB by KT. KT is the basic, K is the Boltzmann constant, T is the temperature. Okay. So if ESB is more, it means that less number of electrons would be able to cross the barrier from left to right, and the current because of that, because of electrons from crossing from left to right, will be less. Similarly, the current due to electrons crossing the barrier from right to left, from this side to this side, will be dependent on the barrier height from the right side, which is EDB, and if this barrier is more, the current will be less, barrier is less, current will be more. Okay, so this is a very I would say this is true very heuristically as well, and the net current IDS, which is essentially the difference between ILR, left to right minus right to left, so let us see, this ILR is equal to some constant C times exponential minus ESB by KT. Okay. Similarly, this IRL will also be C times exponential minus E dB by KT. So the net current IDS, which is the difference between left to right minus right to left, it is equal to C times exponential minus ESB by KT minus C times minus E dB by KT. Okay. So if we take C times exponential minus ESB by KT out, it will be 1 minus exponential minus EDB minus ESB by KT. And this is ILR, which is here. And now there is an interesting thing to observe here. The barrier height from this side is this, the barrier height from this side is this. The difference between the two barrier heights is essentially the VDS voltage, because it is because of the drain voltage that the barrier on the drain side is increasing. So this barrier on the drain side is equal to barrier on the source side plus Q times VD. So this EDB minus ESB will be Q times VDS, so it will be exponential, this term will be exponential minus Q VDS by KT. Okay. So that's how we obtain IDS is equal to ILR into 1 minus exponential Q VDS by K in times T. Now the charge in the channel or the total charge in the channel is because of the electrons coming from both sides. So the total charge right at the beginning of the channel on the source side, let's say at the height of the barrier, at the peak of the barrier is, that is because of the current from the left side and current from the right side. And if you recall, the relationship between the current and the charge is this. Okay. So if this average velocity, if at the peak of the barrier, this is taken to be the thermal velocity because there is no electric field, this will be Qn times Vt, which means that Qn will be I divided by W times Vt. So the charge coming from the left side will be ILR divided by W times Vt, and the charge coming from the right side will be IRL divided by W times Vt. So that way the total charge will be, if we take the ILR out, it will be ILR divided by, so let's quickly do it here. So this total charge Qn at the top of the barrier is it is the charge due to the left side plus the charge due to the electrons coming from the right side. If we take this as a common factor outside, inside we will have IRL divided by ILR. So this factor is essentially this parameter. So this will be, ideally this will be ILR divided by W times thermal velocity into 1 plus exponential minus Q VDS by KT. Okay. So that is the total charge at the height of the barrier. It means that from this expression, this ILR can be written as Qn times W times Vt divided by 1 plus exponential minus Q VDS by K times Vt. Okay. So if we put this expression, this ILR value in this equation, let's say in this equation, so the net current IDS will be W times Qn times Vt into 1 minus exponential q VDS by kT divided by 1 plus exponential minus q VDS by kT. So, this will be the net charge that will be there in the system. Oh sorry, this will be the net IDS as a function of VDS. Apart from this, this Qn we have not yet sort of deduced. So, if we also, so this Qn will also be dependent on VGS and VDS, and typically this Qn in an N MOSFET is given as minus Cg VGS minus VT, where Cg is the gate capacitance or the capacitance of the device looking from the gate side. Generally it is assumed to be the Cox, but it is not actually equal to the Cox. It also, we also need to take into account the depletion capacitance of the MOSFET. So, in some cases when we are not doing the rigorous treatment, it is written down as Cox, but it should be Cg. And this thermal velocity, this depends on the temperature and other things. So, from this expression we can see what is the relationship between IDS, VGS and VDS. So, this is the typical, or I would say this is the IV characteristics which include both output characteristics and the transfer characteristics, and this can be derived right from the very simple arguments, the arguments that we can take from the barrier controlled device picture of the MOSFET. Okay, I hope this is clear, and if not, let me quickly review it. The current, because of the electrons coming from the left side to the right side, is ILR, which is dependent on the barrier height from the source side. The current due to electrons coming from the right side to the left side is dependent on the EDB, which is the barrier height from the drain side. The net current is given by the difference of these two currents, where if we take ILR common, this is the factor left. Now, if we look at the total charge, especially at the height of the peak of the barrier, that will be due to both electrons coming from the left side and the electrons coming from the right side. So, so that is essentially Qn at x equal to 0 is ILR divided by W times Vt into this, and if we put this ILR value in terms of Qn and Vt in this, we obtain this expression for the current. Here it might seem that this IDS is independent of the VGS, but it is not so, because this Qn is pretty much dependent on VGS and also VDS in some cases. So, this current is intricately dependent on both VGS and VDS, and in a way this captures both output characteristics and the transfer characteristics of the MOSFET. Apart from this, this Vt is also important, which is the thermal velocity at the peak of the barrier. So, this picture is quite different from the conventional picture of the IV characteristics of the MOSFETs. Now, let us see, so now this one part is left out, that is the subthreshold, the IV characteristics in the subthreshold regime. So, that is what we will try to understand right now. So, if we sort of zoom out only this part of the characteristics, if we plot IDS versus VGS, moreover not only IDS, we plot log IDS with decimal basis, log 10 IDS as a function of VGS. In that case, by doing that we can zoom out the subthreshold part of the transfer characteristics. So, if we do that, this is what we obtain. The characteristics, this is the Vt, below Vt, this is how the IV characteristics look like. And these characteristics have been drawn for two VDS values One is for VDS is equal to 0.05 volts, which means a very small VDS, and this is drawn for a large VDS. Okay. Now, first let's see the IV characteristics only for VDS is equal to VDD. In that case, so there are two important things that we need to understand. One is, even if this VGS is 0 and we have a large VDS in the system, so at this point when VGS is 0, even then there is a very small current that flows through the device. And if you remember the barrier picture, this is the barrier source, drain, side. So even if this VG voltage is 0, in that case there will be a non-zero probability for some electrons to cross this barrier and reach to the drain side. Although the probability for electrons on the drain side to cross the barrier will be extremely small, almost 0. So there will be a very small current that will be due to electrons crossing the barrier from the source side, and that current is known as the off current, because we expect the MOSFET to be off at this value, at VGS is equal to 0 value, and this is known as the off current. Similarly, in the similar terms, when VGS is VDD, the highest value, quite above VT value, threshold value, and VDS is also VDD, so IDS when VGS is equal to VDD and VDS is also equal to VDD, in this case it is known as the on current. And IDS when VGS is 0 and VDS is VDD. VDD is the maximum voltage, this is known as the off current. Nowadays it is of the order of, VDD is of the order of 1 volts. Okay. So we have an off current, we have an on current, and below the threshold voltage, so if we draw this line, the threshold voltage line, the slope of this curve, this tells us about the subthreshold swing, because this regime below VT regime, when VG is less than VT, this is the subthreshold regime, and the slope here, this will tell us about how much would the current change if we change the VGS by some value. If we are changing VGS by delta VGS, then by the slope we can deduce how much will be the change in IDS, and in this case this will be how much will be the change in log 10 IDS. And see, this slope is known as the subthreshold swing, and this tells us about the gate control on the device. This tells us about how well the gate is able to control the channel, and that's what we will discuss in a bit more detail in the coming class. So I recommend you to look into the subthreshold characteristics of MOSFETs in your UG textbooks, and then in next class we will start our discussion from this point onwards. I thank you for your attention. See you in the next class.